So everybody's been talking about complicated algorithms or, I don't know, very smart software message passing interfaces. I will be talking about the underlying hardware and interconnect performance that makes all this happen, basically. So behind every HPC cluster you see, there are a lot of cables and cards. Those are, most of the time, have to be tuned in order to get the best performance for the HPC to show or to use. So depending on the application running on the system, it may be necessary to tweak the system itself or the network interface card and other parameters on the motherboard. While software and hardware bugs are also expected to occur, we see bottlenecks in clusters due to these two types of needed configurations. Either you may have a wrong configuration on your system, or some bug in a cable, or a switch, or an HCA. So I'll be showing some basic common tuning parameters and debug procedures that help my team, an application engineering team from Mellanox, to improve the performance of the InfiniBand HCA and to try and root cause possible performance pitfalls that may cause your HPC not to run at its best performance. Please note that different server and network adapter vendors may have different configuration recommendations, but the general notion of the tuning and debug procedures should be similar. So, moving on, we divide the tunings or the necessary tunings that need to be done into two different areas. One of them is the single system itself, looking at the PCI Express capabilities, tuning the NUMA nodes, memory configuration, BIOS settings, and power management tweaking. After that, after we verify every system is running at its best performance, we need to validate the network itself. Node validation, the subnet manager, the InfiniBand subnet manager, validating that the network is error-free, not having bad links, bad cables, etc., and running at the expected link speed and width with the cable validation used with the IBDagnet tool. There are not many tools in the OFED package. IBDagnet is probably one of the most used tools, enabling us to get information about the subnet and the cables on the subnet and other hardware specifications. So, first thing I want to talk about the PCI bandwidth limitation. So on a Gen 2 system, we have a PCI bandwidth constraint of around 27 to 29 gigabits per second, while on a Gen 3 server, we'll have, on an 8-lane, we'll have around 52 to 54 gigabit limitation, which means that when inserting a card that should run at a QDR rate of around 32 gigabit per second, we are limited by the PCI on a Gen 2 server. Limits us at 27 gigabits. We're not limited on a Gen 3 server, having us reach the maximum bandwidth that the QDR card supports. On an FDR 56 gigabit capability, we see that on a Gen 2 server we're still limited, and also a Gen 3 server will limit us at the rate to the rates of 52 to 54 gigabits per second. So basically, it's not hard to see that, or let me say that differently. We've met a lot of cases when we deal with the Gen 3 technology where cards do not come up at the right speed for, I don't know, for some reason. Usually it's very complicated. And so what we do, we just use the basic LSPCI tool to verify that the card had gone up in its correct speed. I will show you right now the effect of a PCI card that is being retrained to a Gen 2, and you will see the limitations, the bandwidth limitations. 1 second. This will be a bit slow. So, okay. So what I have here is a server that is installed with a Gen 3 card capable of running 56 gigabits per second. I will retrain the link to run at a lower speed, and we will see the bandwidth is not running or not reaching the needed performance. Running a simple OFED test, IB write bandwidth. I don't know if everyone is familiar with that. This is a simple RDMA test. So I'll be running, 1 second. I'll be running the client and the server. And what we get here is, okay, so what we see here is around 51 gigabits converting the megabyte per second to gigabits per second. We get around 51 gigabits per second on a Gen 3 server. I still owe you, I told you the limitation is around 52 to 54, so I owe you 1 gigabit more, and we'll see how we reach that with further tuning. So I have some scripts here that retrain the link to a lower speed. So I'm going to degrade the link, the Gen 3 link to Gen 2. Using the LSPCI, you can see the capability of the card on this register in the configuration, the PCI configuration space, and the speed that it actually came up with, which is Gen 3, and also a mask that indicates that we have 8 lanes. After retraining the link to Gen 2, I have the lower speed indicated right here, while the capability stays the same. And I get an indication from this tool we have that the PCI link speed is at 5 gigabits per second, while the card supports 8. And the performance degradation is seen right here. You see that we have dropped to around 3,500 megabytes per second, which translates into around 27, 29 gigabits per second, which is the limitation of the PCI Gen 2. Retraining the link back to PCI Gen 3. The performance comes back to what we've seen earlier, which is around 51 gigabits per second. So moving on, to the configuration. I told you I owe you around 1 gigabit. So the NUMA node. So from Wikipedia, non-uniform memory access. Basically, a processor can access it is a computer memory design used in multiprocessing, where the memory access time depends on the memory location relative to the processor. Under a NUMA, a processor can access its own local memory faster than non-local memory. So for the Intel Sandy Bridge micro architecture, we can see that the Sandy Bridge has an integrated PCI Express controller. Thus, every PCI adapter is connected directly to a NUMA node. So on a system with more than one NUMA node, performance will be better when using the local NUMA node, which the PCI adapter is connected to. So we have certain tools or methods of seeing to which NUMA node your adapter is connected to. For example, I will show you again on this system. Before I tweak it, I will try to find out to which NUMA node my card is connected to by doing, let's Let's see if I have it here. Yep. So I'm just cutting out the sysclass net IB0, the device, the network device that is attached to the NUMA node, and I see I'm using NUMA node 0. By using task set, I can attach the process to run on the specific core. To watch the core mapping, core to NUMA node mapping, I will use LSCPU, although of course there are other tools to use, Linux tools. LSCPU shows me that I'm running on the even-numbered cores are running on NUMA node 0. The odd-numbered cores are running on NUMA node 1. So as I saw, my card is attached to NUMA 0. I will try to task set the process to run on a certain core. This is a single-threaded process, so I will run it on a single core. We will see whether it improves the performance that we get. So by using the task set, I basically get the single gigabit that I was missing. We see right now a better performance when running, when assigning the process to run on the node or the NUMA node that the card uses. And basically right now I'm reaching almost the limits of the PCIe interface, reaching about 53 or 52 gigabits per second. Okay, so moving on to some more tweaks and configurations that we can make. I have here some tuning for the AMD architecture. I'm not that familiar with that, so I apologize. On an AMD architecture, there is a difference between a 2-socket system and a 4-socket system. In order to identify which NUMA node is the adapters running on, one should look if the BIOS supports the proper ACPI feature, et cetera, et cetera. I will just go over that. Another thing to look at is the C states. So basically, to save energy when the CPU is idle, the CPU can be commanded to enter a low power mode. The C states are the low power mode states. These states are numbered starting with C0, which is the normal CPU operating mode, meaning the CPU is 100% turned on. The higher the C number is, the deeper the CPU sleep mode. More circuits and signals are turned off, which basically is prolonging the time it will take the CPU to go back to C0 mode. This also affects performance on some applications. Also, some operating systems override the BIOS power management configuration and enable C states by default, which may result in higher latency. So to resolve that, we have all kinds of options in the bootloader files. For example, we have the grabconf here, adding the following kernel parameters into the bootloader command. And this is how we can basically disable entering other C states than C0. Of course, this will take more power and more things that people are trying to avoid, but we are trying to get the best performance we can. And this is also known to help us do that. Another thing is, of course, to check the CPU frequency. Again, check the CPU is running at its maximum frequency. If not, of course, we will get lower performance. So I don't have an example for those two things that I've talked about, the C states and also the frequencies, but I can assure you it also helps us in tuning and getting better performance out of the system. General system configurations also include memory configuration. For higher performance, it is recommended to use the highest memory speed with the fewest DIMMs. This is a thumb rule. I don't have any deeper information or further insight on this, but you should look at your vendor's memory configuration instructions to try and get the max performance out of the memory. Also, this is an example of a BIOS settings. Looking at an Halem-based processor, we found that tuning it into performance mode and also disabling C states, maximum performance on the CPU frequency, memory interleaving is off, socket interleaving NUMA gets us to the best performance. Again, this may differ in different BIOS and also different systems, but the general notion is the same. So moving on to the network configuration. So all of this is basic stuff, but again, we found that on very complicated systems, a lot of bugs or cases end up with wrong kernel wrong driver versions or other simple stuff. So that's, again, this is a recipe of validating the node's condition. Actually check the nodes are responding, have the same driver versions on all nodes, see that the HCA, the host channel adapter, is attached to the driver and has the expected firmware version, and validate the port state after the subnet manager goes up, see whether it's active or down. I know this is all trivial, but believe me, we've seen a lot of cases where people come to debug a very large system, which eventually ends up in a node that just does not operate correctly. Here we have the fabric cleanup, a recipe that basically we do after we bring up a large cluster. We zero all the counters using the IBDAGNet --PC. Wait X amount of time, check for the errors which are exceeding, or check if the errors are exceeding the thresholds that we set. I'll show the thresholds in the next slide. Fix the problematic links. Usually it's reseating or swapping cables, replacing switch ports or HCAs, etc. And going back to stage one of the loop and doing this over and over again until we ensure the fabric is clean of errors and running correctly. Okay, so here we have, I'll show you some thresholds that are set by the spec or by Mellanox, actually. So thresholds are for link speed and target bit error rate dependent. For a QDR link with an expected bit error rate of 10 to minus 12, according to the IB specification, the threshold should be 25 seconds per error. For an FDR link, it's around 7 hours per error. Again, this is the thresholds that we look for when we bring up a cluster, and this is what we set in order to determine the cluster is clean and capable of running the applications needed, etc. Looking at the link down and link retrain counters, these should be zero. A non-zero counter a non-zero counter may indicate a flapping link on the fabric, which is disastrous for MPI-related applications. Receive remote PHY errors also indicates an issue, symbol errors or receive errors on the remote port. People come to us with questions about VL15, dropped packets. In most cases, this counter should be ignored, as these are MAD packets, management datagrams, that are received and before the link is actually up. These datagrams are used to negotiate the link. IBDAGNet helps us with some options to validate the link speed and the link width also, which might cause bottlenecks in the cluster. Link speed, we have the flag, the --ls, specified the expected link speed. Otherwise, the IBDAGnet will shout or show us whether there is an error or not. Link width is the same. Mellanox has also, in its own version of the OFA driver, we have a plugin in IBDAGnet that helps us to diagnose cables. As we've seen in earlier presentations, cables can be also a real pain when bringing up a cluster. So we have the get cable info flag, and which indicates whether gives us information from the memory inside the cable, indicates the cable's capabilities, serial numbers, etc. Subnet manager optimization. The subnet manager is basically responsible for managing the fabric, checking all the links are up, and handling the routing on the fabric. So in order to optimize and check for issues with the subnet manager, we have the sminfo command, just checking whether the subnet manager is currently running, or sometimes we get the port if there is no slave subnet manager and the port of the node that is running the subnet manager suddenly drops, everything will stop working eventually. So this should be run occasionally on the system. Check there are no errors on the SM by looking at the SM log. Select the correct routing algorithm using the OpenSM-R with the routing engine. Sorry, there is an error there. The routing engine parameter in the OpenSM file. For factory or up-down routing algorithms, a GUID file may be needed in order to specify the nodes that are being used as routes. GUID file is simply a text file with a list of GUIDs, of the node GUIDs, global unique IDs, which have the highest hierarchical switch ASICs. One should validate the routing, whether the routing had succeeded also in the OpenSM log. It has different messages that tell us whether the routing had succeeded or not, whether we have credit loops in the fabric, some issues with the connectivity, etc. I will not talk about one of the most important things, which is QoS settings, quality of service, SL2VL mapping. You don't want your storage traffic to be colliding with the compute nodes traffic, etc. So you have the QoS capabilities in InfiniBand. I think tomorrow they will discuss the MPI capabilities with the using the right SLs, service levels to service level to virtual lane mapping. This is a whole different topic that we could discuss for a long time. So right now we'll show you a network configuration congestion example, just by simply having this kind of setup where I have on the same server I have two different HCAs trying to send each other, again using the IB-Write bandwidth test, trying to send traffic over between two switches. I will disable one of the links, disabling one of the links between the switches while running the RDMA test will show us the SM reconfigures the routing to be divided between the ports, and we'll see the bandwidth is being divided equally. Reducing the link width on one of the switches, the SM does not get into a heavy sweep state, which I'll try to explain. When disabling a port when a port falls down or drops in the cluster, the SM does a heavy sweep, which means it goes over all the routings and reconfigures the routing. But doing when the link width just drops and the port is still active, the SM won't do a heavy sweep, and you'll see basically the traffic still flows from a single server to another server in the correct bandwidth or in the expected bandwidth, while the other servers on which the link width had dropped will get the performance drop. I will drop the link from from 4 lanes to 1 lane, and you'll see the performance is being divided by 4. Second. Sorry. I'm using QDR interfaces or QDR HCAs, so I'm expecting to see QDR speed or QDR bandwidth on both cards. So I ran the RDMA test on one pair and on the second pair. Looking at the first pair, I see the expected bandwidth of around, I think, 27, between, again, the PCI limitation of 27 to 29 gigabits on the first pair. On the second pair, I see the same thing. Using a tool, an OFIT tool called IB Link Info, I get the mapping of all the, this is actually quite ugly, but still, I get the mapping of all the cluster and the connectivity. So these are, right here we see the connections between the switches, the 2 ports that are connected. These are, the width is 4 lanes. I will just, at first, disable 1 port using IB port state. It's another tool to control the fabric ports. So right now, I disabled 1 link between the switches. And we will see the subnet manager has rerouted the traffic to run on the same port, and we see the traffic divides into 2 on both interfaces. So this was expected as the OpenSM did a heavy sweep and changed the routing. I will re-enable the port. Again, a trap is sent to the SM, notifying it the port has come up. It'll take some time for the link to be negotiated. We expect to see the bandwidth coming back to the expected performance. And there we go. So again, the SM did a new routing and got us back to the state where we get the needed performance. Let's say for some reason the link width had gone down on a certain port. We'll have to reset the link in order for it to be negotiated at the lower link width. Sorry. So I'm waiting for the link to come back up. It'll take some time. And eventually I expect the performance to be okay for us for one pair and to be cut by 4 on the other pair. I see it come up. It had come up in a, no, sorry. It had come up in the 4-lane width. For some reason, I didn't manage to take the width down by 1. Give it another try. Still not up. Okay. So right now we have a link width of 1, and the performance we get, the SM did not reroute anything. The performance we get for the pair that uses the healthy link is the expected performance, while the performance we get on the reduced width link is reduced by 4. And that's what we expected to see. All of these things can be seen in the IBDAGnet output. So for example, right now I'm resetting the counters, and I will try to run IBDAGnet. And as we can see, we get a width check and an error indication of the width in the log files. I will be able to see the expected, or sorry, the exact report of the width that has been gone down. Let me see if we see it here. Okay, so over there we see at the top, we see an indication of an unexpected width. The actual width should be 4, but it's at 1. I will go and look at the counters right now, and we'll see the congestion that is seen on the port. So basically, we see the exmit wait counter on the node that is trying to send the information, send the packets, and is being congested by the port that is not capable of running at the speed that the node is trying to send. The HCA is connected to the switch on a healthy link that is enabled, QDR healthy link, and the link between the switches is reduced to 1 lane. So we have the exmit wait counter incrementing. You can see the incrementation here, indicating us that there is a congestion on that path. I don't know why this happened. So anyways, this is basically the way that we can see, or the indication of congestion in the cluster. Going later on to debug this, we need to check the path on which the traffic flows. This is a very simplistic view of, or example, sorry. Usually it's much more complicated. These tools are OFED tools being maintained as an open source. And these are not the most advanced tools that we know or have. For example, Mellanox has a fabric manager that enables the user or the administrator, the network administrator, to see everything with a GUI, get much more information on the health status of the nodes and the cluster itself. Of course, you can write scripts that use these tools. There are many more tools, but still everything is not that well developed. But in any case, trying to see basic congestion on the cluster is pretty simple. And that's it, basically. I will show you right now another tool that we have. We talked about the cables. So IBDagnet has the feature of having plugins inserted into it. So in Mellanox, we have the Get Cable Info plugin. Enabling us to see all the cables and the information about the cables being utilized in the system, in the fabric. This helped in previous presentation talking about the cluster bring up. We had seen a lot of cable issues that were discovered and caused performance issues on a cluster. So basically, Mellanox engineers used this tool to trace down the cables and check whether they are from the same batch. Eventually, it was discovered that a bad batch of cable, a bad wafer caused the cable chips to be erroneous and making the cables improper to use. So here we see the information about the cables being connected to which link, indicating the port, the lead, the vendor, product number, serial number, the length. Is it a copper cable or an optical cable, an active cable, the supported speeds of the cable. Sometimes we can see, erroneous implementations or deployments where coming to connect an FDR link with a QDR cable, getting us QDR speed on that link. Users just scratch their heads and don't know why, and it's a real simple problem or a real simple solution. Just swap the cable with the correct cable. But again, usually users think of when dealing with very complicated systems such as high-performance computing clusters, users usually tend to think of much more complicated reasons for issues on the cluster. But as from past experience, I can say it all comes down to, usually it all comes down to some hardware issue. And this was an issue that we've also encountered, just using the wrong hardware on the cluster. I think that's it.